can use the ANSYS environment for structural analysis. You can use ANSYS for thermal analysis, as well as you can use for fluid flow analysis. And finally, yesterday we saw that present design process, which involves not only or it will not restrict to only simulation part. So after simulation, nowadays we optimize solution. In fact, nowadays we optimize multi-physics problems also. So in optimization, it also initially two steps are involved, like an initial feasibility study. So whether whatever the input boundary conditions we are giving, or the inputs given to the problem, whether through that whether we'll get the feasible solution or not. So that is initially checked, and then we perform the sensitivity analysis. So in a given problem, suppose there are hundreds of variable factors. So out of that, more relevant or the more sensitive parameters we can filter through the sensitivity analysis. So in sensitivity analysis, we have two types, like a local sensitivity analysis and the global sensitivity analysis. So whereas in global sensitivity analysis, suppose there are 3-4 variable factors which are involved in the problem, so interdependency is also calculated, or the effect is measured using the global sensitivity analysis. Whereas in local sensitivity analysis, effect of one parameter is only analyzed on the whole system. So with this, you can filter, you will come up with the few countable number of finger countable numbers of variables. And these variables now you can further use for optimization purpose. So as I told you, optimization is nothing but the finding best possible solution from the available set of range of parameters and the input conditions. For example, you may have a different materials, you may have different geometric parameters, you may vary the dimension like a length, diameter, or bend radius, etc. So dimension you can consider the parameter, and the third parameter can be the operating parameters. For example, in a problem in flow through pipe, suppose I am changing the velocity of air. So by changing the velocity of air, I can consider as a parameter. So suppose I am interested to know if I change the velocity of fluid from 100 to 200, so what will happen? So every time you need not normally what we do in a standalone simulation, we change the run the one simulation, and again for next simulation what I will do, I will change the velocity and again run the simulation. So instead of doing such iterative operations, you can consider it as a parameter, operating parameter. So consider it as a parameter, so define as a parameter, and then simply give the range of parameter and the step size. So the rest of work will be done by the ANSYS software. So this way, the parameter can be another, you can import from the CAD, previous CAD softwares also, and also you can define parameters as mesh size also. So in mesh independent analysis, normally, or mesh independent analysis, what we do, we go on changing the mesh size from coarser to fine with certain size, and at every size I will check the responses. So if that response, there is the change in response is not much, then we say that the problem is now, or your solution is mesh independent. So here instead of doing this manually, you can create mesh as a parameter. So you can give the mesh size as a parameter and ask software to change mesh and give me the final result. So this way, these are the different. You can see the different level we can work. So not only for simulation. After simulation, you can go for the sensitivity, and finally, you can say the optimization. So this way, the ANSYS supports complete solution for your problem. Now today, in this problem or simulation, we have seen basically there are three parts of the compartments of the solution. The first one, you can say that's the pre-processing. Then second stage is the solution settings, and third one is the post-processing. So in this, the first part is very important. That is a what you can say, the pre-processing. So in pre-processing, we define geometry, we create the we convert, we discretize the model, and we give the boundary conditions. So this boundary condition and define the fluid property also, material which we are using, like a solid, it may be solid or fluid or both, combination of those. So these things we should give the input as like in nature the actual the things are going on. So out of that, boundary conditions are very important. So if you don't give appropriate boundary conditions, whatever the solution you will get, you may get it may not be correct one. For example, now in in a system or in the given problem, air turbulence or the fluid turbulence is taking place. But if you do not consider turbulence effect in the solution, then you may not get the exact solution. Even that, yesterday one of the participant question which turbulence model is to be used. So it depends upon the flow condition and the given problem, and the whether is the internal flow or external flow. So there are many parameters based on that. These turbulence models selections depends, and even if you select a particular turbulence model, again it will ask few more input parameters. For example, intensity of turbulence. So by default it will take 5%, but in your case it may be 10% or 20% or 15%. So you should give the appropriate inputs, then only you will get the exact outputs. So in today's session we'll try to understand few boundary conditions and then shift to the 2D conduction problem. Yesterday we have solved simple 1D, or we have seen only through tutorial how to solve the 1D conduction problem, diffusion problem. So today we'll try to see 2D conduction, and then finally we'll conclude with the transient analysis. So yesterday we have seen 1D steady state analysis only. 1 minute. So as I told you, the boundary condition, giving appropriate and exact boundary condition is very important part in the simulation, flow simulation. So to define problem that result in unique solution, you must specify dependent flow variable at the domain boundaries. So if you define the boundary conditions poorly, it will have a significant effect on the solution. So appropriate boundary condition must be applied. So here now boundary conditions involves what boundary condition is. So what type of input parameters it involves. So basically what type of boundary conditions we have to apply, that we have to decide. For example, it may be inlet, it may be wall, or if I am considering a symmetric object, if I am doing the analysis of symmetric object, so whether there is a symmetry of axis symmetry or periodic symmetry, so that I should consider or while giving the boundary conditions. So we should simplify the model if the because to reduce the your computation cost. For example, if I wanted to analyze the flow distribution of a ceiling fan, so instead of considering 3 fan blades, I will consider only 1 fan blade. Only one portion and rotational symmetry. So only part of that I will do analysis, and then results I will rotate with the help of revolve feature. So here identification location also important. At what location exactly now the boundary condition is to be applied. So and supplying required data depending upon the type, location, the physical. So once we identified the type of boundary condition, we identified the location, then the next part is supply appropriate data for the boundary condition. So this choice, now selection of the boundary condition depends upon, as I told you here, the geometry. So if, whether it is an axis symmetry geometry or periodic symmetry geometry or any other type. So our objective is to reduce our computation cost. So this boundary condition depends upon the geometry, then the availability of the data, suppose now at inlet pipe, that if you can measure the velocity of air, so data is available with the help with you at experimental data. So that data you can give as a boundary condition. So you can decide that this is the exact location of the location to give the or decide the boundary conditions and numerical considerations also. Now, what are the available boundary conditions available in ANSYS Fluent? So here we can categorize in different two groups, that is the internal boundaries and the external boundaries. So in external boundaries, generally we use pressure inlet and pressure outlet. And for incompressible fluid flow, we consider velocity inlet and outflow. Whereas compressible mass flow inlet is considered as a boundary condition, and normally pressure far field, that is whenever it will go to the atmosphere, equal to the atmosphere only. So pressure far field is considered as a outlet boundary condition. Then other boundary conditions depends upon the, as I told you here, geometry. So depending on your geometry, you can define further boundary conditions like wall. So there is no heat transfer taking place. If you do not consider give any boundary condition to the your problem, so automatically the software will consider that as a wall boundary condition. Now other boundary conditions like a symmetry boundary condition, axis boundary condition, or periodic boundary conditions. So these things we can give. We'll see few examples later in further slides. Now, the first boundary condition normally we use, that is the velocity inlet. So, few of them I am explaining here. So, what is required information for velocity inlet? So, normally you can see here the tab where the momentum, thermal radiation. So, all these tabs will be available for all different types of you can say the inlet boundary condition. So, you have to select the zone name. So, at what location you are supposed to give the boundary condition. So in meshing or in geometry modeling itself, you can define the give the names to the different faces. Yesterday we saw left and right. So left and right of the tube. So or a wire. So we should give that certain namings for the certain geometry entities like faces or vertex or edge, or you can say the whole solid body also. So once you give these names, so these names will be automatically whenever you do the boundary condition. For example, here inlet face. So in modeling itself, I had given somewhere inlet face as a boundary condition given as a name, one of the face. So that will be now that will be available while defining the boundary condition. So you can select the zone name, at what zone the boundary conditions is applied. So appropriate name you should give. Now velocity specification methods. So here what are the different information required while velocity? So magnitude is required, like here velocity magnitude 20 meter per second. So you can define it, may be constant or it may be variable. Even you can define your particular function accordingly, that velocity will flow through the system. Then here components also given. So sometimes the velocity is passing not along the principal axis x, y, z. So sometimes it is suppose entering into systems through certain inclination. So we can define the boundary condition through the components also, magnitude as well as direction. So you can define both magnitude and direction through component system. And the other properties, boundary conditions, like in velocity, if your fluid flow is the condition is the turbulence type, so you can give the turbulence quantities and thermal conditions also. So here you can see at bottom thermal turbulence intensity. So intensity is normally by default 5 to 10%. So you can vary that also. So velocity inlets are intended for use in a incompressible fluid. So normally we recommend for incompressible fluid flow analysis, and generally for compressible fluid flow it is not recommended. Then pressure outlet. So here also gauge pressure. Now you can see here the gauge pressure. Again, it's a function. Then the coordinates that you can select the direction vector, or you can select the component. So x, y, z direction how much the pressure is there. So specified pressure is also there, and this is suitable for compressible and both incompressible fluid flow. Then wall bondage, as I told you, the for viscous, sorry, for viscous flow, no slip bonding conditions. You can define the here the wall boundary condition. Now, in this case, you can also use or shear, apply the add the shear stress as well as roughness value if you are dealing with some turbulence flow analysis. Suppose the flow through pipe water, where the internal surface is, you can say that after usage of that pipe for a long time, it become rough. So the roughness factor also you can consider for simulation. You can give here the roughness value. Then other boundary conditions, as I told you, to simplify our computation cost, we can use like a symmetry boundary condition, then axis boundary condition, then periodic boundary conditions. So in symmetry boundary conditions, you can see, suppose now if I am considering the simulation of the boiler tube or the whole boiler shell or the pressure vessel, so I will consider it is a now example of axis symmetry. So only I will consider a quarter portion, 2D axis symmetric problem. For example, here you can see, or the simple take the example of pipe, flow through pipe. So instead of doing the flow through pipe analysis 3D, so I can consider only 2D part and rotate. I will do the simulation, and finally I will see the results. I will rotate about the rotation axis. It is exactly similar to the feature which you use in CAD modeling, revolve feature. So in revolve feature, what we do, we draw the 2D sketch. We draw 2D sketch, add axis of rotation, and then rotate about the axis to get the cylindrical compound, axis symmetric compound. So similar way here, to reduce our computation cost, what we do, we draw only 2D sketch, do the simulation, and after simulation we can rotate the results on the axis to see the effect. Now in symmetry condition,
मतलब कब तक सबमिट करना है? आज ही करना ना?
Hello, in symmetry boundary condition, no inputs are required. Hello, flow field and geometry must be symmetric.
नहीं, हमें तो आदत आपको ही पता चल गई होगी। डेडलाइन में आज ही जमा करना सारा, आज ही चाहिए। कई बार ऐसा हुआ है ना, बड़ा रहता है।
Hello. So in
Professor Chougule, 1 minute. Somebody is disturbing us.
चांस की बात है सर कि दो तीन मेल मेरे पास भी आ जाती है जो सर के पास कॉमन होती है, लेकिन सर को नहीं पता कि मेरे पास भी आती है। अरे आज लास्ट डेट है, और ठीक है सर, हो जाएगा फिर।
Yes, I have muted him.
So in symmetry boundary condition, or normally we apply in CAD terminology, what we understand, symmetry means it is a geometry symmetry. But in simulation, flow field as well as geometry must be symmetry. Flow field as well as geometry must be symmetry. For example, you consider one vessel, and through this vessel, from both ends, the inlet velocity is entering into the system. So the diameter of pipe, that geometry must be same, but the velocity, suppose at one end the 10 meter per second is entering, and other end 5 meter per second air is entering or fluid is entering. So we can't, or we don't say that this is the CFD point of symmetry. So for CFD simulation or the analysis simulation purpose, flow field as well as geometry, both must be symmetry. And then the other boundary conditions, normally we use like a periodic boundary condition. They may be rotational periodicity or translation periodicity. So you can see the example of here 2D tube heat exchanger. So it's the example of translation periodic So I can only do the simulation of one, and then further I can copy the results. And axisymmetric, like example rotational periodics, you can see here the example, one of the example. Now to enable, now this is about the boundary condition. Now today we are going to cover unsteady state analysis also. So just I will explain the first part of the transient analysis. So now yesterday we solve the steady state problem. So in unsteady state or transient analysis, with respect to time, our results are varying. So we have to define, or we have to select here in the general tab, setup or zone, general tab, you have to select the transient as an option button. That is one part, and then you have to select the time step size. So normally, how many time step size we define point, that is the step size, the 0.01, and number of steps are suppose 500. So here in each step, how many iterations are to be calculated. So number of iterations also we define. So what are the options available for transient analysis? Here the number of time steps and maximum number of iteration per time step. So if I consider here as a 20-second simulation, so in initial time, if I consider 0 and final time I consider 20 seconds, and time step I consider 2, so definitely 20 divided 2, you'll get a number of time steps is equal to 10. Now in one time step, again the software will solve many number of or several number of iterations here. So each time point must be iterate and converge to solution. So here in between 0 to 1, so the problem must converge, then only it will go next. So here transient simulation is solved by computing solution for many discrete point in a time. So we consider time step and give the number of iteration for each time sub step to solve the unsteady state problem. Now selecting the time, this delta t, time step size, is very, very important. If you refer these two figures, so the actual true solution which we are getting is the red color, whereas the blue color is the actual iteration going on depend on the delta t. So if I do not exactly consider step size smaller, so the actually your simulation may not match to the true simulation or the true solution. So here you can see I am decreasing the delta t in such a way that the actual solution trend and the ideal trend both are matching. So normally you can say the smaller step size can resolve the true solution at least 10 to 20 delta t per thread. So if I am considering 2 seconds, in that I have to solve 20 to 30 iterations. Now today we'll see first of all the 2D tutorial on the 2D conduction, and then 1D transient analysis. So I will open. Yesterday we have seen 1D diffusion problem, steady state condition. So today we consider initially 2D Cartesian computation domain, which is square 1 by 1 meter, and the material which we are using is a steel plate, and which is having these properties. Now to solve this problem, we will consider different boundary conditions, different cases. So these cases are shown here. There are 4 cases. So here in first case, we'll take a simple example. Just a minute, sir. Manisha. हॅलो, नाही तुम्ही ट्युटोरियल सोडवा, माझं एक मीटिंग चालू आहे. सांग. हा नाही ते कालचे स्विफ्टचा ट्युटोरियल सोडवा सांग. Okay, so here in first case what we are considering 4 boundary conditions. Those are the temperature boundary conditions: 100, 200, 300, 400. So this, not all of you know that this is a simple example where it is very easier to validate the result also. So if I consider this square plate, and if I take 100, 200, 300, 400 as a temperature boundary condition, we know the result. If I connect the boundary diagonal line, if I connect these two vertices diagonal with the diagonal line, on this line the temperature profile will be exactly 250. So when you solve this, you try to check it. You draw the line passing through the diagonals and draw the temperature profile. So definitely you will get it a straight line of 250 degrees Celsius. So for that purpose, we consider initially simple case whose results, experimental or analytical result known to us with the help of thumb rule. So we are not considering heat generation, so therefore 0. In second case, we are using different types of boundary conditions now. Here the one side, the bottom side is insulated. Then the right side, I am giving certain type of flux, 10,000 watt per meter of flux is giving, and on top side, convection heat transfer coefficient we are giving. So we combine different types of boundary conditions. Second case. Now in third case, only we are adding heat generation. We are adding the heat generation. So in the A case, and B case, it's a replica of B case only. Only we are adding here the heat generation. Now here, whenever we try to solve this problem, it need not require to do the simulation every time for separately for all these 4 cases. You can do once and simply copy paste and make changes, edit. So that we'll see how to do that later on. So see, initially I will show the results. For first case, you can see the temperature distribution. Then for second case, 4 different boundary conditions we have given. So this is the result of second boundary condition. So you can, after this session, you can try to solve and cross check the results. This is the third case, and in fourth case, where we are considering the heat generation. And then discuss the effect of volumetric heat generation result of both the boundary conditions. So that is also we can find out the effect of heat generation on the result. Now, how to solve this problem? Just we'll go through the tutorial. I will quickly go through and finish. So initially, open the ANSYS Fluent. From the ANSYS analysis system, you can simply drag and drop. So automatically the 4 subsystems or cells will become, because in analysis system standard templates are available as we discussed yesterday. So just I will drag and drop here. So these question marks symbols indicate that some data is required. So attention is there. So initially you should import the geometry or create geometry, then discretize it, then set up and define the solution parameters, and finally see the result in post processing. So geometry, either you can right click and edit geometry, or you can simply double click. As I told you, in ANSYS you can create geometry using 3 type of environments. Either you can, if you are using the APDL, you can create geometry using bottom up approach, and if you are using ANSYS workbench, either you can use the design modeler or space claim software. So whenever you double click, by default I think it will open with the space claim now. But if you want to work with the design modeler, right click and select appropriate option. Now when you enter the design model, then you have to create the surface or geometry on a particular plane itself initially. So you'll select the, here we'll select the, by default these 3 planes are available and origin is available. So we'll select the XY plane and go into the sketcher environment. So in sketcher environment, we'll draw appropriate sketch. So here is a simple square. So I'll use the rectangle option and draw the rectangle here. Then if here you can see it is not coinciding, the line which is not coinciding the axis. So you can, if you want to coincide it, you can use these geometric constraints also, and using that you can make the geometry fully constant. Once it is done, then you can give some dimensions like h1 1 meter I am making, and L, that is a second dimension. Now here, click on the concept surface from. Now we are interested to create a surface model. Now just we have drawn a rectangle which is a wireframe model, but we are interested to create a surface. So to create surface, you can click on the concept and select the surface from the sketches and create surface as shown. So you can click on the concept surface from sketches. So we are interested to create surface now with the help of wireframe entities. So I have drawn only rectangle. So I have to convert. I wanted to convert it. You can see in the surface from the sketch. So again, nothing but here we are doing what you can say, we are applying the bottom up approach only. I created only initially 2D geometry, and now I am converting into surface model. So directly you could and then I will create it, if required I will create it a solid model. But if you refer or if you use the feature based modeling software, what we can do, we can directly create a block, or we can directly create a cylinder solid. So when I create a block, it will consist solid as well as surfaces as well as 2D entities. Now here it's a simple case, therefore we are considering only surface. So I will create a rectangle and then convert this into surface. Now to convert this into surface, it will ask to select the objects. So I have to select the select the four sides of the squares and then click apply button. So it will convert it now, it will be converted into surface model. Now the surface is created. Now once surface is created, we need to define the now names of the boundary conditions. So we need to apply boundary conditions here. For example, first case 100, 200, 300 and 400. So I must define, I must give the names to the these entities. So as I told you, the entity can be 2D entity like line, curve, point, or it can be surface, or it can be solid. So here I am interested to apply boundary condition at the boundaries, not the lines. So I have 4 lines sides. So give the names to the sides of the square. So how to give the names? You can simply select the entity and right click, and at bottom you can say the named selection. So when I select the left line and right click, you will see the option name selection. You click the name selection, then in name selection it will ask the name, so you will type the left. Similarly, you select the bottom line, bottom, right, so you can select all and give the appropriate names. So once you give this, so in surface model you can say, if you expand the surface model, you will see the names of the line or names of the sides, top, left and bottom, right. So this is required to define the boundary condition. If you don't have these names, then where you will whenever I apply the boundary condition, it will ask the location. So for defining location, you must give the name, appropriate names. So these names, so see here, geometry can be, here I have selected geometry as a one edge. I selected the edge and give the name, appropriate name. Now once this is complete, geometry is ready, then you can go for the meshing. Double click on the mesh, you will enter the meshing environment. So normally the default settings you can do, there are so many parameters actually in your FDP. Professor has maybe explained the details about the mesh parameters. So here the sizing is the important. We can define the sizing parameter. So like a reliance center may be finer or coarser. Then here you can select the, if you want to select the maximum face size, what should be the maximum face size, that you can define here. You can limit the meshing size, as well as other parameters like mesh parameters like here the angle, curvature, normal angle. All these initially you keep default. Then inflation is also not required. So other options are not required right now for this simple problem. So you will get the generated mesh here, generated mesh. So if you select here the mapped face mesh, so it will you will get the uniform. So there are different sizing meshing methods like sizing, contact sizing, or refining, or other way. What you can do, you can suppose I wanted to have here 100 cells, or the 100 cells on this line. or uniform on all sides. So what you can do, you can select the line and ask software to divide this line into number of divisions, and then you can go for the meshing. So to control the mesh, there are different ways actually. For inflation also, you can use the inflation option in the meshing. So once the meshing is done, then you will enter the setup. So normally for simulation, we prefer the double precision accuracy, and then click OK. Then you will see here the in solution setup, there are different. There is a button like a check also. You can check the quality or the quality of the mesh, report quality. If you click report quality, it will give you the quality parameter with the different quality parameter, show the quality of the mesh size. And then you can select the solver parameters like a default, pressure base, and velocity volume. Normally we select absolute. And here now, as I am working on the what you can say the 2D space, so you'll consider planar option. If I am dealing with the axisymmetric problem, you can select the axisymmetric option. And for solution, as we are solving here steady state problem, you keep as it is default option. And then for example, see in the report quality, if you click report quality, you can see here the quality, different mesh quality parameters like orthogonal quality and overall aspect ratio, then minimum orthogonal quality. So these things you can see, or your quality mesh quality you can check immediately by clicking the report quality. Now here we are interested to solve only energy problem. We are solving the conduction problem. Therefore, we will select only energy model. But if I am dealing with the like solar energy simulation, so you will consider here radiation. So, or if I am dealing with the steam problem, then I multi-phase problem, multi-phase option I will select and make it on. So, which models will be active for your problem, that you can decide here. Now, once I select the appropriate model, according to that model, whatever the boundary conditions are, those will be filtered, and you can see only those boundary conditions in the further simulation. So here I will select the energy simulation only, because I am solving only conduction problem. So I will select only energy option. Okay. Now, once we select the model, then you have to define the material. So as is the material is steel, it is given property. So here through this you can order the material property or materials with the name or chemical formula also. So Fluent is having a huge database which cover all solid and fluid materials. Also here there is a one tab you can see user defined database. So you can define your own fluid or own material also. So you can create it and save it. Now once I select particular model material, here you can filter out. So the type of material like a solid or fluid. So depending on, you can filter the database, and accordingly the properties will be visible to you. So here, as I am selecting a solid, you will see density, specific heat, and thermal conductivity. And then you can create it. Now click on the cell zone condition, select the solid model which is created. Now I am interested to select a particular material. So through this zone, you can select and select the appropriate material. Now we have to give the boundary condition. So we consider first case where 100, 200, 300, 400. We are giving to left, bottom, right, and top boundaries, and there is no heat generation, or heat generation is 0. So I will go into the boundary condition, click boundary condition. You will see here in zone, different zones. So unless and until, see, if I do not create these zones in the geometric modeling environment or mesh environment, I will not be able to give the boundary conditions, because here it will, whenever we apply the boundary condition, it will ask the zone name. So we must define these zones earlier, either in geometry or in meshing environment. So in any environment, you can either you can define geometry, or in meshing environment I can name these zones. So once I select the boundary condition, you will select the appropriate zone. For example, left, So left we are supposed to give the temperature boundary condition. Select the temperature boundary condition and enter 100. Enter 100 here. So these properties are available in thermal. Now as see, if I click here radiation, nothing will be visible because I have not selected model radiation model during simulation. Only I selected energy model, therefore only you will see the thermal. So if I am selecting fluid properties, momentum, click momentum, so you will not be visible because I have selected only thermal model. So appropriate boundary condition, you can give 100 and you can see, select here the material name. So if suppose the if I am selecting the different materials and which is the composed object is combination of different materials from both different ends, so then you have to select appropriate material. So here there is only single material, therefore I will select a solid one, which is a steel, and select OK. Similarly, you select other boundaries, and luckily here all boundary conditions are temperatures. So just go on entering the values 200, then 300 for right, and at top you will enter the 400. And then click the solution method, change. So you can do the some algorithms. Sorry, this setting solution methods. You can select different. Normally we use the scheme. Select the simple scheme only, and energy model. Normally first order or second order upwind scheme is selected. Okay. And now what we are interested to monitor, change in residual. So residual, here the residual convergence criteria I set as a 0001. So unless and until the previous result and the current result variation is less than this, then it will go for the next iteration. So there are two criteria. Either you can set the number of iterations, for example 1000, so it will solve 1000 iterations and stop, or you can set condition, the convergence criteria. So unless and until this criteria is arrived, it will go on solving the problem, and it will, you can monitor on the screen. So here the velocity and energy equations. So you can residuals, you can select the which residual you wanted to plot. So as I told you yesterday, if you want to plot monitor a particular location temperature, so you can define the in geometry itself, you can define the datum point, and that datum point you can add in the residual monitoring. So you can add here residual monitoring. So that that point at that point you can monitor the results or the residuals. Okay, and then you can initialize the problem. So normally in numerical method we assume something, we take something initially, for example 0, x is equal to 0, and then try to solve. So for solving numerical problems, we must initialize, or we must assume some input parameter initially. So you have to click here initialize button. Then after initialization, you can run the simulation. So you can set here number of iterations. Initially you can take a simple 100, and further if you want to refine the model, then you can go on increasing the number of iterations, see the results. And then once you've done calculate, you click the calculate, so it will start running the simulations, and iteration wise it will show the you can say the residuals. It will plot the residuals. You can see on the screen these residuals, and after convergence it will give you the message that the problem get converged. If it is not converged, if something is problem, then it will stop, and then you can resolve the problem. So this way you can see here, the once you solve the problem, you will see the tick mark against the geometry, mesh, setup, and solution. In front of all these cells, you will see the green symbol tick mark. It indicates that your problem is solved, get converged. Now to see the results, you can double click on the result. It will take you into the CFD post. See, whenever I double click with each cell, it will take you in another environment. It is not remain in the same environment. When I click on the double click on the geometry, it will take you the design modeling environment. When I double click on the mesh, it will take you the meshing environment. And now once we solve it, if I double click it, it will take you, see here, fluid flow CFD post. So it will take you to the CFD post module. where you can see in the at top you can see the various contours. So this symbol is the for seeing the contours. So you can click on the contour, you can give the appropriate name also. For example, case A, I can give as a case A here. Uh, Case A, and then click on OK button. So here now we can apply the symmetric boundary conditions also here. So with the help of symmetry location, symmetry boundary conditions, suppose this is the portion where I can do the only half portion simulation and then reflect the images. So once we have got the result in first case, you can, as I told you, 100, 200, 300, 400 at diagonal, it will be 250 degrees Celsius. So to cross check your result, this is the thumb or you can say the shortcut method. Through that you can cross check. You can draw a line here and in post processing plot the temperature on the diagonal line. So definitely you will get it's a 250 degrees Celsius. So in second case, it is very similar. Only here the boundary conditions are previous compared to previous. The different types of boundary conditions are added together here. One is temperature, other is wall boundary conditions, third is the heat flux, fourth one is the heat transfer coefficient. So simply you can either you can now see here for case 2, I need not again create geometry, I need not again create do the meshing setup, solely solve the problem. So what I can do, I can simply copy and paste. I can copy this template here. Now you can see the fluid flow, fluent, copy of fluent. So just by dragging, dropping here, you can copy the simulation. Now once I copy solution, at solution stage, you can see the different symbol. It indicates that it has now it is to be updated. It is to be updated. So to update, before updating, we have to change the boundary condition. So I have to click on the setup, double click. So here for bottom, I will give the heat flux, thermal, I will consider heat flux. Then for right, I will give the heat flux, enter the 10,000. Then for top, I will consider convection. Here I will write the convection coefficient, and here free stream temperature, that is the atmosphere normally 30 degrees Celsius, and then you can again solve the simulation. So how to solve the simulation? You can right click again here, the right click on the solution and click run button. So it will solve, and once it is solved, again here you will see the symbol like a green tick mark that indicates that your problem has been solved. And then through post process environment, you can see the results. You can plot the contour of temperature. In third case, only we are adding here the heat generation. So yesterday we have seen how to add the heat generation. So simply click, go into the sail zone condition, and now you have to select the surface body. Zone is now, see, the heat generation is taking place on the whole body itself. So I have to select now boundary condition, not only 2D entity like a edge. I have to select the surface body. So through whole surface body, I am in the heat generation. So select the surface body and then source term and enter here. Check box the source term and then enter the 50,000 unit. That is a watt per cubic meter, and enter. So with this, what we have done, we have added the heat generation rate, that is a 50,000 watt per cubic meter, and then again solve the problem. So you can see here the red portion. So red portion indicates the higher temperature. So as I am generating or here adding the heat generation rate at center. So normally here I apply what you can say the zone, I select the surface, but heat generation will be exactly at the center. Heat generation rate will be at center. Now similarly for fourth case, you can add the heat generation as a 10,000, see the plots. So this way you can solve the problem. So I have written this tutorial very simple way. Just you go through the software and try to solve this problem. And also I request you, already Professor Sevadkar sir has explained the whole numerical solution using finite volume method, conduction. He might have covered all the part like conduction, convection part. So you try to solve it manually, or you write a code for that and solve it, and then you can compare with the ANSYS results. So analytical as well as you can say the numerical method, numerical technique, and or writing a particular code or using professional software. So you can compare the results using analytical, how much it is coming, then using numerical method, how much it is coming, or professional software, how much it is. So you can cross check your results. Once results are okay, then you can play anyway and to optimize the solution. So that is the normal procedure. Now we'll cover the remaining part, that is a unsteady state problem. So yesterday we covered 1D diffusion steady state. So in unsteady, as I explained earlier, only you have to give the time step details and select the unsteady option in the solution method. See, if you see the yesterday's tutorial and today, both are very similar. Both are very similar. Only here the input parameter is given for unsteady. Number of time steps you have to, here it is given 500, maximum iteration per time step is 20. So in each step there will be 20 iterations, as I shown with the help of graph paper on the graph in PPT I had shown, I think. See here. So in one time step, how many iterations? 20. I am giving as a setting. I am setting here the 20 steps per time step. Number of iterations per time step I have given as a 20, and number of time steps 500. So 0 to 500 time steps, and in each time step you will have a 20 iterations. So 20 into 500, around 10,000 iterations will be, total iteration will be 10,000. And the time step size I am giving as a 0.1 here. So the initial steps are very similar. I will not repeat again and again. So you go into this edit geometry, or you can transfer edit geometry or double click and create model in unit system, then create geometry, and then once you mesh it, and once you mesh it, you go into the you give the appropriate names like a left, right in this case, and then here you can select the setting. You can choose the meshing window and double click, and so there once you double click on the window, so automatically you will enter the setup workbench. Where in setup workbench you can select here now in general option, you can select the transient as a option button. So by default it is always steady state. So you can select now, as we are interested to perform the unsteady state analysis, you have to select transient option, and then you can select appropriate unit, make the energy model on, define the material property, and then you can give the appropriate boundary conditions. So for only B and D, the heat generation rate is there. So in sales hole condition, you can tick mark the source item so that this energy source will be enabled, and you can enter here the energy source. Now here in this case there is only one energy source, but in some application you may need to apply at different location different energy sources. So here you can change number of energy sources. By default it is 1. For example, at 3 location I am giving the energy resource source as a boundary condition. So here you can select enter the 3. So you can define number of what you can say the energy sources. Once you give this, and then rest part is very similar to previous one, only, and then solve it. So before that we have to define the time step also. So in run, when you click on the run calculation, maximum iteration you will set as a 20, and here you can define the time step. I am defining time step as a 0.1 second, and number of time steps 500. So and number of iteration per time step I am selecting 20. So it will record, or it will record all these iterations in the text form. Finished, one time step is over. It will go for the next time space. So this way it will solve the problem and then see the results through the contours. You can plot the temperature. Now color scale, and in here you can select the location. So which geometry? So I am interested to define the location, all the domains. Which variable you interested to plot? I am interested to plot temperature. I will select the variable as a temperature. So here you can use the different scales also, color scales also, different color scales to see the results. Just try with the different options, and finally you can see the result. So compared, this is about the steady state and unsteady state analysis, conduction analysis only, conduction analysis only. So I think from my side it is over now. Sevatkar sir. Sevatkar sir.
Yes, sir, I'm there. I'm there.
I have finished, sir.
Okay. There are few questions actually. I mean, if you could answer those questions, that will be. Sir, first question is, what is the difference between hybrid initialization and standard initialization?
Hybrid. See, actually, I am not having that knowledge. I will check it and let you know. See, there are many options. Actually, I am dealing with many softwares. Presently, I am not in touch with the CFD software.
Okay.
That's why I may not be able to answer right now. Definitely, I can answer tomorrow.
Okay. So there is another question. How can we reduce the iteration time if more number of elements are there?
Pardon?
How can we reduce the iteration time if more number of elements are there?
Iteration time. For same number of elements. For same number of elements.
If the number of elements are higher, he says that the time is larger.
Yes, it will take definitely.
Can we reduce that time by doing something else?
Doing something else, that inflation you can do. For example, flow through pipe. So so coarser mesh is required at center, but at boundaries where the solid fluid interface is there,
we can make use of non-uniform boundaries.
Non-uniform.
No, non-uniform meshing. Non-uniform
meshing. Yes. And even we can select the higher order elements, like we can go for polynomial elements instead of linear. There are different ways, like in P method. Normally there are two types of simulation: P type of simulation and H simulation in FEM. So normally what we do, a polynomial method, where instead of changing the number of elements, I will change its order or degree of element. For example, I will instead of linear, I will go for quadratic, I will go for cubic or higher order element of the same configuration, like a brick element. In brick element, how many nodes defined by the help of 4 and 4, 8 nodes. But if I go for higher order, definitely you can reduce the computation cost, and the number of by keeping the same number of mesh size, you can get the solution quickly and accurate.
There is another question. Does the ANSYS provide location of the specific temperature, for example, 250 degrees?
Yes, definitely. You can locate particular with the help of datum points, and at that particular point you can find out the temperature or any property. Even you can define your own variables also, as I explained yesterday. For example, I wanted to know the Nusselt number. So with the help of heat transfer coefficient, I can define my own relation also, and I can monitor these at any location. So, but for that, initially you have to define some geometries, like you need to define datum point or line or any other surface patches. So at particular location, if you are interested to your interest is at particular zone to monitor the result or find out the result, then that is possible, sir. Very much possible. Even you can extract the data. Suppose this contour plot I have plotted, I can extract the data in 2D in CSV file, Excel file, and from that Excel file I can get the textual data also for further analysis if I wanted to do or compare with the experimental results. So you can extract the results in textual format, graphical format, or in what you can say the video formats. So in post processing, many capabilities are available, and if these capabilities are not available in the or your requirement, as per requirement, you can take help of other tools like a take plot. You can extract the data, post processing data, and in take plot you can play. Okay, sir. Should I close?
Hello, Chougule sir.
Sir.
There is a question. I want to plot a temperature with respect to time when hot oil is immersed in the water. That is transient state. How you can help to do it?
Right now, without ANSYS, it is difficult to explain through the. Actually, these things are possible.
It is possible. I mean, you have to capture the. I will answer the question.
And those things
Professor
are possible.
Professor Harinath. Yeah, it is. You have to capture the temperature data at various time instances, and then you can look at the transient behavior. It is possible to obtain that. I mean,
so same data is software generated, and it will show you in the monitoring phase. It will show in the graphical format. So in reverse way, you can extract the data in a CSV file, and then you can find out the textual data.
There is another question. You are giving 4 boundary conditions, fixed temperature, and high volumetric heat generation. If we don't know one boundary temperature, what to do? If you don't know the boundary condition, you cannot solve the problem. It's as simple as that.
Yes.
For solving
for
solving two-dimensional problem, Professor Lijo, you need to know 4 boundary conditions at least.
So software will automatically consider all boundary condition. If you do not give any boundary condition, automatically software will consider or it as a wall boundary condition, sir, and solve.
There is a question by Rajnikant VK. Sir, there is one option, steady and transient. What is the use of that? How it will affect to CFD result? Actually, it's not possible to get. I mean, I'm not able to understand the question asked by Professor Rajnikant, but let me answer it. That it is. Sir, there is 1 minute. For steady and transient, what is the use of that? See, transient problem, we study to understand the transient behavior. For example, let us say you are carrying out a heat treatment problem, Then during heat treatment, how the temperature changes, that is very important. If you are not able to keep control on the changes in the temperature, you cannot heat treat the product appropriately. So it is important to know the steady state behavior and transient behavior. And steady state behavior, you must know. I mean, there are many processes which are steady in nature. Or if you look at the time average data, you get the steady state behavior. And from that steady state behavior, you can understand essentially the physical phenomena which are occurring.
So normally, sir, what we do, we start with the steady state problem. But naturally, actually, it is an unsteady state problem, any problem. So initially, we simplify the problem and consider as it's a steady state condition, solve the problem. Once we solve the problem, then for final tuning, we go for the unsteady state condition. Go towards the actual natural condition, you can say.
If the problem is unsteady in nature, your result will be different. So, and many times it is essential for us to learn the transient behavior.
Yes, sir.
I hope Professor Rajnikant, we have answered your question.
Sir, sorry, sir. Can you repeat once again?
See,
Hello.
if your problem, many of the problems in the nature are intrinsically unsteady in nature, and for many of the
Okay.
problems, variation in the temperature or variation in the velocity with respect to time is required to be understood, because at various time instances various phenomena occur, and in order to capture those phenomena we must be able to solve the transient problems. But some of the problems may reach to steady state. We can also understand whether a particular problem is steady or not steady by looking at the transient problem by solving the transient problem. So it's important for us to get acquainted with solution methodology for steady as well as transient problem.
Yeah, sir. That was my doubt was in which case we will select a steady and transient. For
See,
all case we can do.
you need to look at the physics of the problem. You need to have a priori idea. Some of the
Okay.
problems are in nature itself or in transient. So for that you cannot apply steady state problem, steady state equations. So it is normally suggested to apply unsteady state equation only. And if your problem is steady, it will automatically reach to steady state, although you are using unsteady state equation. So normally it is suggested to make use of a transient solution methodology only.
Okay. Okay. Okay.
For
Thank you.
general lookout, you can go for steady state, but actually, normally it is unsteady. Na? So, if you want to refine or get the final result in proper manner, so you go for unsteady state condition only. Because in nature, normally, if you see any problem like we have covered this, so it is unsteady only. Now, after 2-3 hours, the steady state condition achieved, we conduct the heat transfer problems. So initially, this temperature goes on changing continuously, and later on they become steady.
There is
So this
another
behavior
question, Professor Chougule.
we can capture through the software.
Professor Chougule, there is a question. I will answer to that. In fact, if I have to solve energy and momentum simultaneously for the case, is it possible at the same time? Yes, it is possible. You can
Yes,
solve
yes.
momentum equation and energy equation simultaneously. Rather, you have to solve it simultaneously only. If your problem is unsteady in nature, at every time instant you have to solve momentum equation, and then immediately you have to solve energy equation. Momentum energy. That is how you have to
Yes,
go
sir.
ahead. And
That's why, sir,
many times when the your flow, suppose your flow involves heat transfer, the heat transfer develops the buoyant forces. These buoyant forces are again required in the y momentum equation. So you have to solve those momentum and energy equation in a coupled form when you are solving heat transfer and fluid flow problem together. This next question by Professor Robo. Is there any possibility of the temperature goes beyond applied boundary temperature due to collision of heat propagates from different sides? Not essentially. The temperature now doesn't go beyond, let's say, if you are using boundary condition of 100, 200, 300, and 400, it's not possible for, it's not possible that the temperature will go beyond 400 degrees Celsius. It's not possible. That should not go. Which programming language to simulate the heat transfer and fluid flow? MATLAB is good. See, the language is the personal choice. You can use C programming language, C language, Fortran language, whatever you are comfortable with. But to the best of my knowledge, the C compiler gives you better speed compared to that of MATLAB. But in MATLAB, you can do the coding very easily. So there are pros and cons of these.
plotting is also
Plotting is
easier.
also possible in MATLAB. That is also possible in C, but in MATLAB it's easier. So
See,
language is the choice. Language is your choice.
It depends upon, nowadays people are using Python also. So it depends upon the selection of software.
It depends on your comfort. Your comfort. I hope, Professor. There is another question. Can you please give us all the ANSYS tutorial files used in both the
Yes,
sessions?
sir. Already I have mailed. I have mailed to you. Please.
I will hand over. I will give it to the participants.
Okay. Thank you, sir.
Is there anything? Anybody want to ask any question? If there are no questions, we shall stop. I express my sincere thanks to Professor Chougule for
Thank you,
sparing
sir.
his valuable time with all of us. His inputs will be definitely useful to those people who are beginners. They should, if they have access to the software in their institute, they must start using ANSYS. Try to solve simple problems like 1D conduction, 2D conduction, 1D and convection conduction problems, and then maybe they can switch over to the solution of entire Navier-Stokes equation. So tomorrow we will be dealing with the solution of entire Navier-Stokes equation. Thank you very much, Professor Chougule, for your valuable time and valuable inputs.
Thank you. Thank you all participants for listening patiently, and I will forward more tutorials also, which we have not covered now, like a combination of conduction, convection, then 2D flow, etc.
Okay.
Thank you, sir. Thank you all.
Thank you all. So we will stop here.
Thank you, sir.
Thank you very much.